this work is all in collaboration with the people listed here. That's Eamon Gaffney, Kenta Ishimoto, Clement Moreau, and Ben Walker. And it's really motivated by wanting to understand the motion of active particles, active swimmers, in the presence of shear flow. So you can consider this, in some sense, similar in scope to the classic Jeffrey's orbits problem of passive spheroids in shear flow. But here the particles are active, so they generate their own force and torque. And to just give you a little spoiler at the outset, you end up finding something that I think is quite surprising and fundamental about the relationship between active swimmers in shear flow and classic Jeffrey's orbits. So in addition to the physical application here, another reason that I'm quite keen to present it is because it requires an interesting modification of a classic mathematical method of multiple scales. And although the analysis ends up being quite technical, I'm going to try and give you a high-level overview of how it all works, and all of the technical details are contained in our recent manuscript, which I'll reference at the end if you're interested. So the key thing that we want to understand is the observed smoother behavior of these swimmers over the timescales of a few minutes. And specifically, how do these smooth trajectories arise from these quicker rotational motions that many active swimmers exhibit over the time scale of a few seconds? There are interesting applications of this. So for example, in synthetic biology, you might want to genetically modify swimmers or create magnetically controlled artificial swimmers in order to enhance or disrupt their overall trajectories by controlling behavior at the microswimmer level. But for the rest of this talk, I'm going to largely focus on the fundamental fluid mechanics question in this problem. So the physical problem that we consider is kind of straightforward to describe, but a bit intricate to set up mathematically. But basically, we're just thinking about a very, very basic model of an active swimmer, essentially just a 3D rigid object that generates its own force and torque. We put this into a shear flow, and we just want to see what happens. Because it's a rigid object, there are 6 degrees of freedom. That's 3 for its orientation, 3 for its center of mass. And then, as Jeffrey did 100 years ago, it's going to turn out to be helpful to define the orientation in terms of the Euler angles. And broadly, in comparison to the lab frame, theta here is kind of the angle it makes with the horizontal. Psi is kind of the spin it makes around its own body. And phi is kind of the yaw, which is the angle it makes in the horizontal plane. And because we have an active swimmer, it generates its own force and torque. And we are just, as a modeling assumption, going to say that these are constant and fixed in the swimmer basis. But remember that the generated torque is going to cause this to rotate around in the lab frame. So even at this point, we are describing nonlinear evolution equations. And then we just put this rapidly rotating swimmer into a shear flow, and we're interested in what it does. And what's really nice about microswimmers, as many people in the audience will know, is that they're tiny. So the flow problem is Stokes flow, and it's linear, and it has nice properties like the reciprocal theorem. And this means that we can include the entire hydrodynamic interaction effect of the flow very straightforwardly in the equations of motion, basically in terms of the far field flow and a couple of rank 3 tenses, H and G here, that essentially include all of the geometric information about the swimmer, its size, shape, and orientation. So this is a very nice compact way to write the equations, but it is worth noting that these tensors are in general pretty horrible. And so to make our lives easier, we're going to consider swimmers with certain shapes, essentially those that exhibit helicoidal symmetry. So you can think of helicoidal symmetry as a kind of discrete rotational symmetry. And in some sense, this is a generalization of axisymmetry, which is a kind of continuous rotational symmetry. So all of the shapes on this page display this discrete rotational symmetry. And many swimmers can be well approximated by this kind of symmetry. And the other key thing that I want to flag here is the idea of chirality in these swimmer shapes. Only the first figure here is achiral. The latter three are all chiral objects. And the idea of helicoidal symmetry allows for both achiral and chiral swimmer shapes. And by restricting ourselves to these kinds of shapes, it massively reduces the complexity of these horrible rank 3 tensors, H and G, so we can actually write them down explicitly. And this was shown by Kenta Ishimoto a few years ago. And essentially, it reduces them down to having only 3 degrees of freedom subject to orientation each. So we can write these tensors explicitly in terms of the orientation, which means in terms of the Euler angles, and 6 geometric parameters in total. And I'll talk about these in a bit more detail later, but basically you can think of B as kind of being a measure of the effective aspect ratio of the object, and C and D as being measures of the chirality of the object. So if the object is achiral, then both C and D are equal to 0. And putting all of this together, which we can do straightforwardly because of the linearity of Stokes flow, we get our full system of equations, now in explicit form. And so for most of this, I'm going to focus on the rotational dynamics because they largely force what's going on in the system. But I do want to flag that everything I'm going to talk about carries over to the translational dynamics, and we have solved everything for both. The details are in the papers. But for now, these are the rotational dynamics of the system. The terms in left encode the fast rotational dynamics generated by the swimmer itself. And these terms on the right encode the hydrodynamic interaction of the shear flow with the swimmer, now given explicitly because we have an object with helicoidal symmetry. And as a quick aside, it's helpful to just remind ourselves that the problem we are looking at is, in some sense, an active swimmer version of the classic Jeffery's orbits problem. So if we switch off the self-generated rotation of the swimmer and exclude any of the chiral effects, we just get the classic Jeffery's equations for passive spheroidal particles. And so Jeffery derived these results 100 years ago for these passive spheroidal particles. And in his results, the parameter B is an explicit measure of the spheroidal aspect ratio. B is positive for a prolate spheroid, it's negative for an oblate spheroid, and it's 0 for a sphere. And then in the 60s, these results were extended to general axisymmetric objects. And it was found, quite remarkably in my opinion, that you actually get exactly the same equations for axisymmetric objects, but now B represents kind of a measure of the effective aspect ratio, just by direct comparison with the classic Jeffery's equations. And I do want to emphasize this fact because it's going to be important to our results, but essentially passive axisymmetric objects behave as spheroidal objects in shear flow, but with an effective parameter B that corresponds to an effective spheroidal shape. We are interested in understanding how active objects and chiral objects relate to all of this. So in our model, we have this, this parameter B that sort of captures this effective aspect ratio, and the chiral parameters C and D. And these coupled ODEs represent the rotational dynamics of the swimmer. And as I mentioned, the terms in the red box are the fast rotational dynamics generated by the swimmer. And these terms are very large, so they dominate. So if they dominate and the effect of the flow is small, you might think, well, why don't we just ignore these small flow terms and see what happens? And if we do that and solve the resulting system numerically, we get solutions that look like this. But if we include the small effect of the flow, we find that the emergent dynamics change hugely. And this is because the problem is singular. So can we make sense of and understand what is going on here? The answer is yes. And in the rest of the talk, I'm going to talk about how we do this and what we find. And it essentially starts by noting that the broad reason this is a singular problem is because our leading order solution is periodic, but the small effect of flow doesn't cancel out over one of these periods. So what that means is that this small effect of flow can build up over a longer time scale to cause significant changes to the overall trajectory. And this means that it's the exact type of problem that can be solved using the method of multiple scales. And this is why we can make a lot of progress in understanding what is going on here. So the method of multiple scales essentially lets us systematically derive a governing equation for the local average of a near periodic solution, essentially generating a governing equation for the red line here. It's a very powerful method. It can be used to understand all sorts of emergent behaviors in many different physical systems. And a significant technical challenge with applying this method to our problem is that we have a strongly nonlinear 3D system. And this means that we need to be quite careful in how we use this methodology. We need to use a slight modification of the classic methodology. And the classic methodology basically involves these 5 steps, and we will need to slightly modify steps 4 and 5, as we'll see when we get there. But the analysis starts as you'd expect. You introduce a fast and a slow time scale, and you treat these as independent. And in doing this, I'm going to introduce a key parameter here, omega, which is essentially a measure of how far away the rotational axis is from the helicoidal axis. So omega is 0 if these two things coincide, which is kind of when the object looks like a well-thrown rugby ball. And it's infinite if these two things are perpendicular, which is kind of when the object looks like a very badly passed rugby ball. And there's a distinguished asymptotic limit when omega is order 1. And we can straightforwardly capture the sublimits from that. So I'm just going to consider omega as order 1 going forward. And introducing the fast timescale transforms our derivatives as you'd expect. So our transformed dynamical system becomes this. And now we just perform an asymptotic analysis. So these red highlighted terms are the leading order terms. So this is our leading order system. And at this point, we need to be a bit careful because we have a coupled nonlinear 3D system. It turns out you can actually solve this system explicitly, which will be incredibly useful for the analysis. And to do that, you first note that the 2 top equations decouple from the third. And then just by messing around with them, you find that you can write these equations in a way that just lets you integrate up directly. So this gives you a constant of integration, actually a function of integration because they're using the method of multiple scales. And this tells us that our leading order system exhibits this fast time conserved quantity h, which only depends on the small time, on the slow time, which is small t. And this conserved quantity here is a non-trivial function of the orientation of the Euler angles in the system. And I'm now going to do something that seems kind of mysterious, but it's going to end up helping a lot. And that is to redefine this function of integration h in terms of this new function, theta bar. At this point, it is not clear why I have done this or why I have labeled it as something that looks like theta. But as will hopefully become clear at the end, this slow time function will essentially be able to be associated with theta in some sense. And then we can just leverage this conserved quantity to solve the remaining leading order equations, and the solutions are given by these 3 expressions here. And the key thing to flag is that these theta bar, psi bar, and phi bar terms are the 3 slow time functions that you get from solving the leading order 3D system. And these would just be constants if we just solved the leading order system without doing the method of multiple scales. In that case, you would just end up with a black line trajectory here. But the way that these things slowly evolve over time that we're going to work out will tell us how the blue trajectory emerges from all of this. And as I alluded to at the start, this is going to tell us something about our system and its relationship to classic Jeffery's orbits. So the remaining goal of the analysis is to work out how these functions of integration evolve over the slow time. And to do this, we get to stage 5, the final stage, and we have to go to the next asymptotic order, which is this. And I'm not going to go into the technical details here, they're in the paper if you're interested, but essentially we have to derive the slow time governing equations we are looking for from this system here. And this is where we need to be a bit careful about the fact that it's a system. often when we teach the method of multiple scales to undergraduates, we say, look for the secular terms, set them equal to 0. But it's not always obvious what the secular terms are. And that's especially so for a system that's quite coupled. And essentially, to get the appropriate solvability condition, you just have to solve the homogeneous adjoint problem and integrate your inhomogeneous right-hand side against this. And I'm happy to chat in more detail at the end about why this is the case, but if it seems weird, essentially it's exactly equivalent to imposing the Fredholm alternative theorem for a system that is periodic over the fast time scale. An additional technical complication is that this system is not self-adjoint, so we can't just leverage our leading order solution. Even so, it turns out we can actually solve the homogeneous adjoint system exactly given by P here, and then we can use this to obtain the appropriate solvability conditions. Then, after doing a lot of algebra, you obtain the solvability conditions that we have been looking for, which are these evolution equations for the slow time functions. So, together with the leading order solutions, these completely explain the emergent behaviors observed numerically. And you can see on this figure here that the two solutions agree really nicely. And then this is comparing loads of different trajectories, all with different parameters. The numerical solutions are the black lines and the asymptotic solutions are the red lines. They generally agree pretty well. So we're quite happy that this sort of shows that we could be confident in our analysis. So this is nice. I love to see lines overlap with other lines. But for me, a reason that I really like asymptotic methods is that they often let you gain deeper fundamental insight into the physical system. So can we get that here, where at first glance, we kind of just have a big block of equations? Well, let's go back to our full system on the bottom left. And the green box here is the effect of the slow effect of the shear flow on the system, which is given by these functional forms on the bottom right, the HIs. And now, if you look at the blue box on the top and ignore the constants in here and just look at the functional forms, on the top left, you have cos theta bar, sine theta bar, sine 2 phi bar. And here in H1, this term here is cos theta, sine 2 phi. And if you look at all of the functional forms here and look at their equivalents in there, they are all the same as the original, just replacing x with x bar. So actually, all of the slow evolution equations that we have derived are just Jeffery's equations in our new transformed variables, but with effective coefficients that we have calculated exactly. So we can write these slow time evolution equations in a really compact form in terms of Jeffery's equations with effective coefficients in terms of the original coefficients, which were B, C, and D, and also in terms of omega, which, remember, quantifies this relative fast rotation axis of the swimmer in comparison to the helicoidal axis of symmetry. So we have found that the effect of rotation is to cause emergent Jeffreys orbits in appropriately transformed variables, but with effective coefficients that quantify the effect of rotation. So the active rotating objects behave as passive objects with effective hydrodynamic shapes that account for this rotation. Importantly, in these appropriately transformed variables. And because these effective coefficients are sort of the key to understanding what our results mean for the effective hydrodynamic shape, it's helpful to think about them in a bit more detail. And so this is the normalized Bretherton coefficient B hat. And remember, omega is quantifying this agreement in some sense between the rotational axis and the helicoidal axis. 0 if they coincide, infinite if they're perpendicular. You can see B hat is unchanged if omega is 0. So if rotation coincides with the helicoidal axis, but it reduces as soon as the magnitude of this, of omega increases and the rotation axis moves off this helicoidal axis. And interestingly, it can even switch sign if the off-axis rotation is large enough. So an active prolate spheroid can behave as a passive oblate spheroid and vice versa. There's also a critical rotation rate where omega is the square root of 2, and this causes the effective Brotherton coefficient to vanish, essentially making these active objects behave like passive spheres. And you get a similar thing with the chirality coefficients C and D. It's kind of a bit harder to show on a static figure because they both depend on each other. But essentially what these figures are showing you is that the magnitudes of C hat and D hat are bounded above by the square root of C squared plus D squared. So we can kind of interpret this to say that the effect of rotation is always to maintain or reduce the overall effect of chirality. But because C hat can individually be greater than C, or D hat can be greater than D, as long as the overall constraint of overall chirality being reduced is satisfied, this means that different aspects of chirality can be over or underemphasized due to rotation. And interestingly, in both cases, it's omega goes to infinity, so the rotation axis is perpendicular. Both effective chirality coefficients vanish, which means that that object starts to act as though it is achiral. And we can interpret this as rotation kind of spreading out the moment of chirality, which is kind of what C and D represent here. So finally, to conclude, microswimmer motion often involves rapid rotation. We have found that rapid rotation gives you these emergent Jeffreys orbits in transformed variables. So active swimmers gain an effective passive hydrodynamic shape. So active prolate spheroids can behave as passive oblate spheroids and vice versa. And we found that rotation generally reduces the overall chirality, but it can overemphasize different chiral effects. And this could explain why some active swimmers behave as though one of their chirality parameters is larger than its measured value. So more broadly, I kind of hope to have shown you that you can still do quite a bit of work with asymptotic methods in the modern era. These techniques really were key to gaining fundamental insight into these problems. So please do check out the papers if you're interested in the technical details. Thank you very much for listening, and can I take any questions?